Now that we're really clear about effect sizes, the next step is to think about how we can tell if a sample size is adequate for a predicted effect size. Surprisingly, there are multiple definitions of adequate in the statistical literature, and this is an area of active development. The most well-known approach is based on statistical power, so let's start there. Planning for power is straightforward. You define your research questions. For each question, you guesstimate the effect size. And finally, you calculate the sample size needed to regularly detect the effect size of interest. Let's consider an example. Is knocking out gene X neuroprotective for induced stroke? You'll test this by inducing stroke in normal and knockout animals, and then measuring their neurological severity score. That's a popular measure in animal research on the global impact of a stroke. To plan your sample size, you need to think about a quantitative issue. How much might your gene mitigate stroke? To make this guesstimate, normally you'd turn to the published literature. So here's data from Zhu et al., which found that knocking out the PRP gene had a very large neuroprotective effect, 1.5 standard deviations. We could use this potentially as our effect size guesstimate. From that expectation, we can use a power calculator, and it would tell us that with 8 animals per group, we could regularly detect an effect this large. I've defined regularly here as 4 to 5 times, or 80% of the time. There are lots of good tools out there for power calculations that can help you do this type of analysis. But unfortunately, there are also some problems with this approach. First, planning for power helps you determine what it will take to succeed. It doesn't help you plan how to rule out an effect or to show that your negative results are interpretable. Second, the plan is very sensitive to your effect size guesstimate. Third, developing an effect size guesstimate is really tricky. The effect sizes that we find in the published literature are likely to be both biased and uncertain. Let's take a look at the stroke study I just mentioned as the basis for my power calculations. In this study, normal animals had an impairment score of about 12 after an induced stroke. Those who had the PRP gene knocked out only had an 8. That finding is statistically significant, and it's large. That's a Cohen's d of 1.5 standard deviations. Remember, though, that samples are not perfect indicators of the truth. We should expect sampling variation. Let's visualize this uncertainty, putting error bars around the difference that represents the 95% margin of error for the effect size. Now we can see that statistically speaking, it is plausible that the real effect is much larger than Zhu et al. Found in their specific sample. It could potentially be as strong as 3 standard deviations. If that's the actual effect size, our sample size plan of 8 is wasteful and needlessly risky. On the other hand, though, the data from Zhu et al. Is also consistent with an effect size of just 1/4 of a standard deviation. If that's true, it would require 252 animals per group to regularly replicate this result. Yikes. Now, those are the values we find at the extremes of the margin of error. We ought to take them seriously, but mathematically, they are the 95% worst case scenario. But unfortunately, even small sampling error can make mincemeat of your sample size plan. Let's say, for example, that Zhu et al. Only slightly overestimated the effect, that the effect is actually a whole standard deviation, which would still be quite impressive. But not knowing this, you went with the sample size of 8 for the 1.5 standard deviation. What would your power be if the real effect is actually just this slightly smaller value? It would become just 0.44, meaning it would be more likely than not that your experiment would fail, even though there is a real and substantial effect to be observed. And that's scary, but also informative. No wonder we can't sometimes reproduce work from another lab, or sometimes even our own lab. It doesn't have to be bad hands or reagents. Sometimes it's just that the original effect was significant, but still uncertain, meaning it would be difficult to use for planning future research. Even worse, we should remember that sample sizes in the published literature are likely to be overestimates due to publication bias. So what can you do? Well, one important step is to obtain what's called an operating curve for the sample sizes that you're considering. That's a plot of the power you would have over a range of effect sizes and sample sizes. And it lets you help make a more informed choice about the trade-offs between more sample size and more power for different ranges of effects. Another possibility is to hedge your sample size plan for both uncertainty and the possibility of publication bias. Ken Kelly and his group, which is at Notre Dame, has an excellent paper on this topic. His team has also released a package for R called BUCS that can help you calculate sample sizes corrected for both bias and uncertainty. And if you're not an R wizard, Ken also has a website called designingsperiments.com. And on that website, there are easy-to-use web applications for planning sample sizes in this way. Here, for example, is the interface to plan a simple two-group design. It's really easy to use. I entered in the data from the Zhu et al. Paper. I used the default value of modest correction for uncertainty and bias, and I requested a sample size plan for 80% power. And Buck says that all I need is 59 animals per group. No, that's not a typo. If you wanted to see for yourself if PRP is neuroprotective, you would need 59 animals per group to have a strong chance of replicating these original published results. Now, how could that be? How could the sample size requirements be so outrageous? Well, first of all, in general, it takes more samples to do good science than we're typically willing to admit. But the other source of the problem is that the original result is so uncertain that it doesn't provide a clear foundation for further research. Go back and look at the original results. We note that the benefit of the knockout is about 4 points. That's the signal. But the margin of error in this study is 3.5 points. That's the noise. This study is statistically significant, but it's very noisy. That's what we mean when we say that a study is underpowered or has an inadequate sample. Statistical significance is great. It means the null hypothesis of exactly 0 can be ruled out. But what can be ruled in? How important is this effect, and how can we study it further? That remains unclear. It's important to look and think carefully about this. P is less than 0.05 does not mean that you have an adequate sample size. Who cares? You can publish it. But think about what happens next. If you want to assess mechanisms of this effect, well, what sample size would you use for your mechanistic study? Totally unclear. Is the practical significance important enough to start thinking about clinical trials? Totally unclear. It could be a breakthrough, but it could be a very slight benefit. What would happen if another team tries to replicate your results? Most likely a result within your margin of error, but much of that margin of error is in a range that would be very difficult to detect. So it's more likely than not that another group would come up with a non-significant finding for your published significant finding. This is probably the most useful part of sample size planning. It helps us see our research results with new eyes.